Hello. I don't think anyone else has joined, so let's wait for some time. Hi, Rohit.
Hello.
Hello. Let's wait for 1 minute, see if Sarangs is going to join. Then we'll start with today's session. Uh, okay, I believe let's make a start because, in the interest of time, we should make a start. So, what you can see on my screen, I hope you can see my screen, is an Excel sheet. And this is where I just wanted to quickly show you all how to do the calculations relevant to the ANOVA testing on Excel. We have already seen a one-way ANOVA test. Uh, how to do that we have already seen, but here we are going to look at the same thing in two different ways. So you can see there are two tabs I have. One is a manual tab and the other one is a data analysis pack tab. Now the data is the same. I've just made up this data. So this data has no relevance, by the way. I'll tell you what this data has been made for, or what is the background. So basis this data, there are two options in which in Excel we can do the calculation. So one option is obviously to do the calculations by hand, and this is something I wanted to show first. This will take around 5 minutes. Uh, and then if we have any queries, we can spend some time in there. And the reason why I'm doing this is because for, let's say, personal projects, we may not have a full-fledged Excel version, right, which is like paid version and all, because I'm not sure if the other option, the one that I'm going to show you, that is related to the data analysis pack, and this is almost similar to what we have done in Python in the last class. The IPython notebook or the Jupyter notebook is already uploaded into the LMS, which you can have a look at. So it's just like or what we have seen in the last session. It was just like creating a function or calling a function with some inputs, and then the function tells you whether to reject or accept the null hypothesis. That's all we were doing, right? So the data analysis pack in Excel is also similar to that. We will be using the data analysis pack in the later cases as well, but as of now, let's go with this only. So let's first start with the manual approach, and the reason why we are doing the manual approach, as I told you, is that not everyone will have access to all the features of Excel. Hence, it is good always, to look into how to do things manually. You will seldom be doing this in a manual way, just to be clear, because we already have all the tools and all the softwares, right, to do these things. So we will really not be doing this in a manual way, but it is good to know. Okay, it is good to know. So it's good. So we will do the calculations first. Okay, and then we will do it using data analysis pack. I will also show you what is a two-factor ANOVA. Very briefly, we are going to discuss that. So that's going to be the agenda today. And then what we can do, we will move on to our next set of things with some clarification. So I know that we had to cover some kind of basics of linear algebra and basics of calculus. In the interest of time, let's do one thing. We will go ahead with the rest of the topics, and then accordingly, we are going to take these topics up wherever applicable, right? So, and then in the similar way, we will take up SQL. Okay, so let's start with this one first. So these are those through three factories. Okay, if you remember the example, these are those three factories which we had, which I own, and because of this corona issue, I'm not able to give salary to all my employees, or maybe I'm not in a position to, not optimize my costs. So I would really like to optimize the cost. So this is kind of a cost optimization problem where I have these numbers are basically, let's say, the daily outcomes of how many specific entities or utilities I've created. Okay, so from factory A, these are the 10 days of sample. From factory B, these are 10 days of sample. Factory C, these are 10 days of sample. Ideal condition, if you are really doing the ANOVA, or for that matter in any statistical test, please do remember that the general rule of central limit theorem applies everywhere. What I mean by that is that general rule should be taken very seriously, and that you must have at least 30 samples. Okay, so for each and every group or each and every area, you must have at least 30 values. Okay, but because we are trying to learn just the mathematics here, that's why we are taking only 10 values. All right. So first of all, what we need to do one-way ANOVA or one factor ANOVA is that we have to take the means first. Okay, we have to take the averages of each and every of the productions. Okay, so to do this in Excel, okay, the formula that we use is the average formula, and we simply select all the cells and we get the average. It's a cool feature in Excel. I'm not sure you are aware. There's a plus sign that comes here, right? When I go to the extreme end of the cell, if I just drag it like this, it expands the formula for the rest of the cells as well. So this cell now shows the average of all the B rows, and this cell now shows the average of all the C rows. Okay. So getting this, you can also verify this from here as well. If you look at the formula at this place, you can verify this. Now, the first thing that we have got is the average. Okay, these are the individual averages of each and every 10-day of production from factories A, B, and C. Let's take a general average of these three numbers as well. Okay, because that will be required to calculate the SSG and SSC. That is exactly what we are trying to do over here. Okay, that's why we are taking these means and all these things. Okay, let me just format these so that they are nicely structured. So these are, I'll mark them with the yellow. These are the means. Okay, so these are the means, and this is the mean of means. Okay, so this is the first step which you do. The first step, you can also write it down or maybe refer to the recording at a later stage so that you can revise the concept. So the first thing is to take the means. Each and every group I have taken the mean. Okay, and then I have taken the mean of means. Again, to stress why this is a one factor otherwise, because I have only one independent variable in this case. Yes, I know I've represented three columns. That doesn't mean I have three independent variables. I have only one. And the one is the outcome, the output, the number of items I'm actually producing from my X factory. Okay. Now that's the first step to do. The second step to do now is that we need to again go back to the basics, and we have to say that I have my F value, which is nothing but I have variance between groups and variance between errors. Okay. So across groups and within groups is what I'm going to consider, right? So variance between groups will be the denominator, will be the numerator, and variance within the groups is going to be the denominator. So variance within the groups comes from the error. So I can represent, as we already know, I can represent that as sum of squared errors divided by degree of freedom of error. Now that we are going to calculate this, we'll come to know exactly what is the sum of square errors. Right. As of now, we were assuming there is some value called sum of square groups and sum of square errors. Degree of freedom we do understand at this point in time, but to understand the sum of square thing is really important, because later on, when we look at the last statistical analysis method, when we will actually start predicting things, right? We are going to start estimating or approximating things. At that time, this will be really important, because sum of square group, sum of squared error, other terms like sum of square totals and so on is really going to come handy. If you don't know the concepts, it will be problem. So the numerator is sum of square groups divided by degree of freedom for the group, and the denominator is sum of square errors divided by degree of freedom of errors. Okay, each and every one of them has a formula. Okay, I'm not going to tell you the formula. Why? Because we are going to do the calculations here, right? So because we are doing the calculation, there is a point of me to telling you the formula, because we are going to do the formula. Okay, so let me just clear the drawings and let me go back to my Excel sheet. And here what I'm going to do, first of all, let's try to calculate the sum of squared groups. Okay, so let's close this and then center SSG calculation. Okay, so first of all, I'll do SSG calculation, then I will do SSE calculation. And basis this SSG and SSE calculation, clearly, I can do, let's say, the F calculation. Okay, so let me just copy this and put it over here. I can do the F calculation. Okay, all the three things we are going to do in Excel only. Okay, and we are going to do it entirely manually. Okay, so what is SSG? SSG is sum of square for groups. A is one group, B is one group, C is one group. Okay, how we calculate the sum of square or groups is we take the mean of each and every group, and even before that we write down the names of the group. We take the mean of each group, okay, and subtract the mean of means from that group's mean and take a square. We are taking a square to get the absolute value. That's how we calculate the variance, right? So in this case, for A, it will be 44 minus 49, and this entire thing should be squared to 2. So in Excel, this is that sign represents square. So exactly that is what I'm trying to do. Okay. In case of B, what will be the case? Simple. 50 minus 49, and there will be a square. The last but not the least, 53 minus 49, and there will be a square. Okay, so this is the formula of calculating the variance. We already know this. We know the how we calculate the variance, right? So this is the formula of calculating the variance in this case, because I have a mean here. I have a sample mean and I have mean of means. So I'm taking the variance like this, right? So this is how you take the mean also. If let's say I have these values, I want to calculate the variance. You will calculate the mean, and individually you are going to subtract 44 from 37 and take a square. That is how you calculate the variance, right? In the same way, for groups overall, I'm only considering the mean value and the mean of means, right? Now that I have got this, what I need to do is I have to sum this up. Okay, I have to take the sum of the variances. Okay, so this is also known as sum of variances, and then I have to calculate the number of items in each group, hash each group. Okay, so the number of items which are there in each of the group. In this case, I have 10 items per group. That is my sample size. Okay, this becomes my sample size. The sample size is 10. Okay, so now that I have got sum of variance and each group members, what I simply need to do is to print the value of SSG value. So SSG value is now equal to sum of the variances multiplied by the number of items in each group or the sample size. So this becomes my SSG value, right? Simple thing. For each and every group, subtract the mean of means from the mean of that group, take a square to get the variance, and repeat that for all of the groups. Okay, you take the sum, take the count of the samples. Here I have 10 samples, so the members in each group will be equal to 10. Do a multiplication, you get the SSG. That is the mathematical formula. Okay, now I have to calculate the degrees of freedom for groups as well. Obviously I need to do that. So quite clearly df of g, uh, sorry, df, degree of freedom for groups, is going to be what? How many groups are there? 3 groups are there. Degree of freedom is always the actual number minus 1, and hence the value is 2. So this part was very simple. Degree of freedom for group is really very simple. The one for errors is not going to be as simple as this, because for errors it is not only about individual values, it is also about the group. Okay, it is not only about the individual value but also about the group. That's why we need to consider both, and that is why we need to do a multiplication, similar to what we have done in case of chi-square test. We multiplied in r minus 1, c minus 1, where r is the number of rows, c is the number of columns, right? So in this case, the degree of error or degree of freedom for errors is also going to have a similar formula. But let's first calculate the SSE, then we are going to look at the degree of errors, right? So for SSE, what we need to do, we have to consider each and every item. Okay, what do I mean by each and every item? Is as simple as this. I take this value, right? I have taken this value from the group A. This is the first value from the group A. The cell number is A2. Okay, so I am going to write a formula over here, and you will understand why I am doing this at a later stage. So I'll write a formula A2. Okay, so I am taking the value of A2, and then what I need to do, I have to subtract the mean of that group, which is this value, A12. Okay, from this, take a square, right? This gives me the value 49, right? If I drag and drop this downwards, what happens is this value is now getting changed. You see, it is taking the next value of A, but it is not taking the same value of the mean. So what I need to do in case of Excel is that this is a very nice trick. You can do a dollar sign over here. Okay, if you do a dollar sign over here and make a drag, now it is not going to change. You see, now it is A3 minus A12. Okay, so I have 10 items. Let me just drag and drop this for 10 and 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, if I do this, I have got the individual variances of each and every item for the group A. I hope you can understand what I'm trying to do over here, right? Let me just cut this and paste it over here, because I think I should write the name of the group as well here, right? Or otherwise I will understand. So this is the way I was able to calculate the variance of each and every item. Okay, now as we know, with respect to variance, what we usually do, we need to take a sum first of all the variances, and then only we can do further calculations. So in the same way as I have this, let me just put this formula over here. The formula is going to be wrong, so I'm just going to correct this over here, and then I'm going to copy this over here again. Again, my formula is going to be wrong, so I'm going to correct it over here. Now if you see the formula, now this is B2, okay, and then the formula considers B12. So this line until from here until here will be for the sample or group B, and this will be for the group C. I can simply extend the sum thing over here, and I get the sum of everything. Okay, let me take a sum of sums, and that is going to be, let's say I'm going to call this margin center, sum of all vars. Okay, sum of all the variance sum is going to be equal to sum of these three numbers, and this is going to be the total variance. Okay, this becomes clearly, this becomes, okay, my SSE value. Okay, this is the sum of squared of errors value for all the individual samples, for all the 10 entries for each group A, B, and C. I took the total. I hope you understood how I calculated it. I have simply subtracted the mean of group A from each and every value of A and taken a square and then taken a sum. Okay, so it is x minus x bar square and sum of x minus x bar square, and it is what I'm taking, and then I'm taking a sum of all these three groups because I have three groups belonging to the same independent variable. That's why I'm doing a summation, and then the total becomes the SSE value. So let me just highlight this into yellow. Now what I'm going to do, simple, again I'll have to calculate the degree of freedom for errors, because that is the denominator of the denominator, right? So that is the denominator of the denominator. I don't know why this is not coming up, so let me just write it like this. Okay, so degree of freedom of error is going to be uh, with a formula which is similar to what we have already seen in case of chi-square test. In case of chi-square test, we did an n minus 1 multiplied by c minus 1, where n was the number of rows, c was the number of columns. In this case, what we are going to do is we are going to do a minus 1 from the rows, but not the columns. Why? Because the variance that is calculated over here belongs to each and every value of the rows. Okay, that is the reason why the formula in this case will be something like 10 minus 1 multiplied by 3. Okay, where 10 is the number of samples. in each group. So I'm doing a -1 to get the degree of freedom of that group, okay, individual group. And then there are how many groups? 3 groups. That's why we have multiplied it by 3. In other way to look at this, you can look at it in other way as well. The degree of freedom for A with 10 values is 9. That of B is 9. That of C is 9. Hence, the degree of freedom of all the values is going to be 9 multiplied by 9 multiplied by 9 is equal to 27. Simple, right? So that's why, or that's how I have calculated SSG. I have calculated degree of freedom. I have calculated SSE. I have calculated degree of freedom for errors, right? Let's quickly jump onto the F value calculation. Okay, what is going to be the F value now? Okay, the F value, as simple as, is going to be 420 divided by 2. Then in the denominator, I'm going to have 3300 divided by 27. This is the formula, right? SSG divided by DF of G is the numerator. SSE divided by DF of E is the is the denominator. SSG divided by DF of G is the numerator. SSE divided by DF of E is the denominator. I get the value 1.71818. I don't know what to do with this value, right? Because either I need a P value or I need a F critical value, right? Only if I get a P value or a F critical value, then only I can do something, right? Because you already know what is the alpha value. Nothing was specified by me in the question. So that's why we are going to assume this is going to be 0.05. Okay. But I don't know the P value. Hence, I am not in a position to use alpha. But at least let's try to find out the F critical value. If I find the F critical value, maybe I will be able to do something, right? So to find the F critical value, there is already a function which is available in Excel. And I'm simply going to call that function, which is f dot inv, right? If I call this function, I have to give the probability as the first input. This is not the alpha value. It is not the level of significance. It is not the alpha value of 0.05. It is the confidence interval. So that means it is 0.95. How much probable I would like to be. Then the second feature, the second input is degree of freedom 1. It refers to the degree of freedom of groups. So I enter 2. The second one is degree of freedom 2, okay, which refers to the degree of freedom of errors. Okay, why is so? Because mathematically we have to calculate the group first and then the errors. The cumulative one, then the individual ones. If I press enter, I get the F critical value. The same thing, if you go to the internet and look at the F distribution table, you will get the same value. Okay, on the internet, you will find the F distribution table. Maybe in the LMS, I'll share the link of the F distribution table that I've already found on the internet, but a simple Google search is going to tell you what is the case. Okay, now using this, you can clearly see the F value is 1.71818 and F critical value is 3.5. 3.35413. If actual F value or the statistic, the test statistic is less than the critical value, hence we cannot reject the null hypothesis. That is the outcome. Okay, let me just write this in bold. We are not in a position, we fail to reject, we fail to reject the null hypothesis. Okay, clearly this is the case. Okay, I hope you have got the point clearly. F value is less than the F critical value. This value here is less than this value here, and that is the reason why we are not able to reject the null hypothesis, unfortunately, in this test. Right? So this is the way in Excel. This is one of the ways in Excel you can do this. Right? So this is one of the way. Now there is one more way. The one more way that I would like to show is if I go to the second tab, which is the data analysis pack, the data is exactly the same. I'm just going to select all the data. Even if I don't do so, doesn't matter, but I'm just going to go to this data tab over here and I'm going to select the data analysis tool pack. This tool pack is enabled in Excel for me. If you don't have this enabled in Excel or if you don't have this Excel software at all, please ignore this. We have already looked into the manual way of calculations. You can do it from there, but then you'll need to remember the functions and formulas of everything. Okay, you have to remember everything related to the functions and the formulas. So a good thing will be to have the data analysis tool bag. I'm sure in your respective organizations, you'll already have uh, the Excel software as well as the functions that you can see in the list in the data analysis tool. Okay. Okay. So in this case, I'm going to do an ANOVA single factor. Please ignore what is two factor with and without replication. We will look into this at a later stage once this part is done. So I'll select ANOVA single factor, and in the next window, it is asking me for an input range. So I click on this box over here, and I give it the input range of the data. Now you note that I have also selected the first row which has the labels. So I will check in this box which says labels in the first row. I give the alpha value over here. Okay. And I simply press OK. If I press OK, this creates a new tab altogether. Okay. With some output. Let's try to see what this output is actually talking about. This is exactly the same as what we have done. Okay, exactly the same as what we have done. There are some terminologies or some things which are different from each other. Okay, only the naming is a bit there. So you see over here there are three groups A, B, and C. Count represents the number of samples in each group. Sum represents the sum of items in those groups, and obviously average is this number divided by the count. Hence you get the average, and you get the variance as well. Okay, so this is the statistical summary. You get the count, you get the sum, you get the average, the variance. Then it is performing ANOVA in this table, and what it is doing, sum of square between the groups is 420. Exactly the same as we calculated, you see. It is 420 over here, and it is 420 over here, degree of freedom 2. The same applies for within groups or sum of squared errors. Now, simply this value, MS, okay, otherwise known as mean squared value, okay, or mean square. You can also call it mean square, right? This mean square value is basically the sum of square divided by the degree of freedom. So if you divide this by this, you get this. Accordingly, the F value is calculated. Somehow it has calculated the P value as well and the F critical value. Okay, there is also a manual way in which you can calculate P value. I have not shown it to you. Maybe you can explore it onto the internet as to how to manually calculate the F value, right? But it is a very simple thing, similar to how we have calculated the F value. The P value can also be calculated, and then you can compare the P value with the alpha value, which in our case was set to 0.05. Clearly, P value is greater than the 0.05, and hence we cannot reject the null hypothesis. Okay, right? So in this way, you see there is an option which is already available in Excel to get the output, and this is really very nice output where we get all the data at one place in a very good way, and we can look at the output and we can try and understand what is happening, especially with these three values, and we can try to understand what is going on over here, right? So this is as same as what we have done. I hope there are no questions here. Let me just rename this DA pack output. Okay, I'll share this Excel in our LMS portal as well. So don't worry. I'll just put this one first and here. Okay. So this is what a single factor ANOVA is. A two factor ANOVA is also similar to this. I'll just quickly show you what it is and what is meant by two-factor ANOVA replication and all these things, so that it is just useful for conceptual things, and then we can move with the next topic. I hope we can extend a little bit of time, and then we can go ahead with the thing. So two-factor ANOVA. Okay, what is two-factor ANOVA, or the concept behind two-factor ANOVA is, as of now, we have only looked at one independent variable. What if I want to look at two independent variables? Okay, so let's take an example. Let's say I have three kinds of, let's say, customers. Okay, and I would like to see if their debts or their pending payments are cleared if I give them discounts. So let's say there are certain customer to which I have given 2% discount. To certain customers, I have given 1% discount. And there are certain customers where there are no discounts. So I'll just write 0% discount. Okay. Now they have some invoices pending, right? They have some invoices pending. So let's say for 2% discount, I have taken 5 cases where 11 invoices are pending. For someone else, 16 invoices are pending. For someone else, it is 9. For someone else, it is 14. Someone else, it is 10. These are either the customers or maybe the distributors who are, let's say, retail distributors who are taking products from me. Okay. For this 1% discount case, let's say the numbers are something like, I'm actually making them up as I am writing here. So they're like, I don't know, 23, then 11, then it will be 16, something like this. Okay. And then let's say the third value is going to be 14, 11, I don't know, 17, and then it will be 16, something like this. Okay. So now I would like to perform a one-way ANOVA test over here to find out what is going on. If is this really my a null hypothesis here is what mu of 1 is equal to mu of 2 is equal to mu of 3. Obviously that is not the case. So am I in a position to accept or reject the null hypothesis is what I would like to see. Okay. Clearly I can perform a one-way ANOVA. Right, clearly we have seen the formula. I can again go to data analysis back and I can perform. But do we have enough support, or do we have enough data to support the idea that our offers changed the average number of or the average number of invoices which are pending? Okay. Or maybe just to take even a better example, let's say these numbers are not actually the number of invoices which are pending. These numbers are actually, let me write them as the number of days for which customers invoice was pending. Okay. So rather than the number of invoices itself, let's make it even more business oriented or even painful thing is the number of days for which any particular customer. So let's say this is C1, C2, C3, C4, and C5. Okay. So some customer C1 given 2% discount still has 11 number of days for which the invoice was pending. So this is C2, this is C3, this is C4, this is C5. So this is one case. And then again, the other cases that have 1% discount, the other cases that have the 0% discount. Okay, maybe I should write it something in this way, that this is C6, C7, C8, C9, and C10. And then here I have C11, C12, C13, C14, and C15. Right? So these are the 15 customers I have actually sampled, and this is what I've got. These are the number of days they took to clear the invoices. Okay. So I can clearly perform a one-way ANOVA test and I can find out whether my null hypothesis is really correct or not. Okay, right? So we can find out what is going on over here. But is that really the right thing to do? That, or is that really a complete thing to do, that I'm only looking at the percentage discount I am giving on your bill, and I'm looking at how many days you are taking to pay back the bill? Is the bill amount also not important in this case? If the business analysts sit down and start thinking about this, obviously they will argue, I would also like to do the analysis based the amount of the invoice. Okay, the amount of the invoice will also play a very important and equivocal critical role in the analysis. In this case, we can't only consider the discount. We have to consider on how much amount we have a discount, right? A 2% discount on 2 rupees is really a very big kind of a discount. Okay, but a 2% discount on 1 lakh rupees is also even more bigger. So I need to know what is going to be the amount. In that case, now you see, I no longer have a single independent variable like this. In this case, my single independent variable, or IV, was simply the percentage discount. Now I am adding another independent variable, which is going to be the invoice amount. Right? In this case, to solve this kind of an inferential statistics problem, I can make use of two-way or two-factor ANOVA, right? So what I do now is that I add a new column here, and I'm going to write the amount. This is the customer ID. Okay, then again, this one was the customer ID. This one was the customer ID. This is just for the explanation that I'm doing it in this way. Okay, ideally, the data will consist of this column, this column, and this column. That is how you need to prepare the data, right? When you are actually doing this kind of an exercise practically, you will have to do the data engineering using NumPy and Pandas libraries that we have briefly looked into. And you will have to select the fields in this way. You will have to later we'll see SQL queries as well. You'll have to write SQL queries in such a way that you extract data out of a database in this way. Okay, that is a very, very big task, very, very important task, right? So but as of now, what we are doing is we are going to consider, as we said, the amount as well. So let's say the invoice amount, I'll just pick some very random and very easy numbers. Okay, 50 rupees, 100 rupees, 150 rupees, 200 rupees, and 250 rupees. Very simple. I have simply selected 5 random numbers. Okay, let me just middle every one of them. Okay, for customer C1, what this table means now is for customer C1, for an invoice amount of 50, if I give a 2% discount, this customer takes 11 days for me to return the money or to pay me the invoice. Okay, customer 6 with 1% discount is taking 21 days. Customer 11 is taking 14 days with no discount at all for a total invoice amount of 50. This is how you can read this table. Now we can do a two-factor ANOVA. Okay, but there are some terminologies that we need to know. Okay, and for that, let me just insert a row over here, and I'll say block. Okay, I'll copy this here, 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 and make them bold. Okay, each and every of these rows, which itself now becomes a group. Why? Earlier you had only 3 groups: 2% group, 1% group, 0% group. Now you have again 5 more groups, right? Each and every group pertaining or referring to a single row. I'm going to not call them groups just to avoid the confusion, because I've already named these as groups. So if I call them groups, what am I going to refer them to? Group 1 and group 2. That is also going to complicate things. That's why I keep these names as groups. Okay, so I'll just insert something over here, and I'll say this is group, this is a group, and this is a group. Okay, this is group, this is group, and this is group, right? But these rows will be represented as blocks. So each and every row I'm going to represent as one block. So this, and this forms one block. This, and this forms one block. And similarly, this, and this forms one block. This, and this forms one block. And 16, 15, and 11 forms one block. Irrespective of in which order you read the rows, right? You see, I have read the rows in a random order. Irrespective of the order in which you read the rows, you get each and every group on the row level as well, which is now known as the block. Okay, this is the only difference of data representation when it comes to two-way ANOVA. Now, how can we do that? Okay, we already know we need to calculate sum of square groups, sum of squared errors, right? We have to total them now because we have another group concept over here. So that's why earlier we calculated only sum of square of groups and sum of square of errors. But now that we have two group kind of concept, one is known as a block and one is known as a group, I have to introduce a new terminology known as sum of square totals, which will be equal to sum of square groups plus sum of squared errors, right? Now, what is going to happen to the sum of squared errors? If I only if I calculate the totals, that total is applying only on the sum of square groups and the errors, right? Now this could have been done using this much part only. I already know I have calculated in the last example the SSG and SSE values when I had only one independent variable. Then what is the need, or what is going to happen to the sum of squares introduced by this blocks? There are 5 blocks, right? So for that, what we are going to introduce again another term is the sum of squared of blocks, SSB. Okay, there is a formula, but I'm not intentionally writing the formula. You don't really need to know the formula. I can share you the formula later on if you want, right? But then overall, the value remains the same, or the f value is going to remain the same. Only the calculation is just going to differ, and the only thing which is going to differ is this: the degree of freedom of groups remains the same. The degree of freedom for error, right? Degree of freedom for error, okay, now is going to become is equal to number of rows minus 1 multiplied by column minus 1. Earlier it was, in case of a single independent variable, it was row minus 1 multiplied by column simply, and we explained that as well why that is the case. In this case we have to do both because we are considering two groups over here. One is called block, other is called group, right? So now that we have got this formula as well, and we have got degrees of error, the formula, the function for calculating f remains the same. Okay, there is no difference between the calculation of f in earlier case and this case. F is still ssg divided by dff of groups divided by sse divided by df of errors, right? Okay, now we are able to calculate the all the other things, and the one thing that I would like to specifically mention is something like this. So there is a relationship between SST, SSG, SSE, and SSB, and you can represent it using something like this. SSE is technically SST minus SSG minus SSB. Okay, this is a very important formula. You must be aware of this. Okay, let me just put this over here. Okay, so this is a very important thing that we need to remember. SSE in total is going to now not only consider SSG and SSE. So I'm going to delete this because this becomes irrelevant, or maybe I'm not going to delete this. Let me just go to format cells and let me go to font, and I'm going to strike it through, because now that I have a concept of SSB, I have to take that into consideration as well. So that's why sum of squared total becomes sum of squared errors plus sum of squared group plus sum of squared block. So a total of these three becomes sum of squared totals, SST. So that's why sum of squared errors can be represented in this form. Okay. Simply put, I can again take the Excel formula, okay, and I can calculate the values, and I will be able to get all the output, right? But I just wanted to show you what is the case over here. Now there is a small complexity that I would like to quickly tell you. What happens if I do something like this? This is just a complexity that I'm trying to introduce. Let me just zoom this out. I hope you are still able to see it, right? So what I'm trying to do over here, let me just, yeah. So what I'm trying to do over here is, rather than having one sample or one sample out of for one customer in one block, what if I intend to have 3 samples? So essentially, rather than taking one sample, I'm taking multiple samples per block, right? So this becomes C1, C2, C3, C4, something like this. Okay, and then I'll say C16, and then I will say this, and then I'll copy this over here. No, I'll just say C31 and something like this, right? So what I am essentially trying to do is, in my earlier case, okay, I had only one sample per block. Okay, but now I am taking more than one sample per block. Why I'm doing that? I'm just trying to generalize my data as much as possible. Clearly, the more data I provide, the more variety of data I provide, I will be able to capture more of variance. And this NO exercise itself is to capture as much as variance as we want. So that's why I'm trying to provide as much variance as possible. So let's say this is the situation. Okay, so for each and every value, I'm just putting the random values, right? As you can see, I'm just doing a +1 and I'm actually putting the values here, right? So 23 is this, 16, 17, and this will be 18, 17, 18, and 19. And then here it will be 11, 12, and 13, right? Each and every one of these now becomes a block. Is that the case? No. The block remains this one only. This is one block. This is one block. Okay, this is one block. Only the fundamental understanding of the block is now going to change, right? Because in earlier case, I had only one sample in the block. I had only this much, right? Let me just make this bold. This was the one which I had earlier. Okay, now what I have is, rather than having one customer, or rather than having 3 customers per block, I was having 3 customers per block earlier. Now I have 9 customers per block. So what I do, I simply take the averages of each and every case. So I take samples and then I calculate the means of means, right? So while I do the calculation, I will simply convert this table into the average. So if you look at the average of this, the average is going to be 12, right? So when I am going to finally create my data table, the data table is going to look something like this, on which I'm going to do the ANOVA, right? So the data table in this case is now going to look something like this. This is 2% discount, this is 1% case, and this is 0% case. Okay, now this block is going to be 12. Why? Because the average becomes 12. This average is what? 22. Okay, this average is what? 15. Okay, I've strategically chosen the number so that they are like this. So this is what? 16, 17, 18. Okay, then this number becomes 17. The next number is 9, right? So this becomes 10. The next number becomes 15. The next number becomes 11. I hope you are getting my point there, right? So this number becomes 16. This number becomes 24. This number becomes 12. This number becomes 17. Again, in the last block, this number becomes 12. This number becomes 18. This number becomes 17, and this number becomes 22. So I'm simply taking the mean value and I am creating the mean of the samples I'm taking for each and every block. I'm going to forget all these things, because anyways in the calculation I'm not going to use the customer ID, right? So I've got the groups, I've got the blocks, I've got it in the same format as the earlier example, and I can now do the calculations. Now what is the difference between this one and this one is only in the name. It is all about the name, right? It's all in the name. The name of this is called two-factor ANOVA with replication, is what the name is. And then I take this and put it over here, and I will call this two-factor ANOVA without replication, right? So that is the only difference here. That's all. There is no other difference. Only the name is going to differ. The calculation ultimately for both is going to remain the same. Right, again we will have concepts like these, and we are going to calculate the degrees of error and the degrees of freedom for error and group. We find the f value, and accordingly we will also find the grp1, grp2, grp3. So we will also find the the value of f. So if I take this, let's just give it a quick try. So if I take this, go to the data tab, take the data analysis, two-factor with replication, right? So without the replication is this one. So I'm going to try with without replication first. Okay, it has labels. The answer is yes. Let me see what value it is going to provide. You see, it has already calculated all my groups. You see, I have 3 groups. It has calculated everything. It has also given me the f values of rows and columns in both the cases. Now I have to look at both the cases. In both the cases, this value is less than f critical value. I cannot reject. I fail to reject the null hypothesis. Addition of the discount, irrespective of how much is my invoice amount, does not do any help for me. So by giving the discount to the customers, like 2% or 1%, did not do any help. Okay, they did not do any help at all. So that is the final outcome that I've got. Right, let me just save this file. Okay, I hope the concepts are clear, right? So if you have any questions, please do let me know. Maybe we can make it a stop here, and in the next session we will continue with the rest of the results. So I'll just DA pack output. I'll just name this like this. I'll save this and I'll upload this into RLMS. Yeah. I think that should be all for now, Rohi. If you have any questions, please do let me know. Okay. Thank you. Good night.
Okay. So,
Yeah.
just one quick question.
Yeah.
This is Excel 2016 or 2019,
Give me 1 minute.
which you are
Even
using.
I do not really remember. So let me just check the version. I don't know which version this is.
Yeah, because I'm using 2007 one, and it does not have this data analysis option.
You
So
are using
yeah,
which one? Sorry.
2007 one.
2007 version. Just a minute. Let me search.
Yeah,
Excel 2007 data analysis tool pack should be there. Just a moment. Let me see. Excel 2007 data analysis tool pack. Yes, it is there. It is there.
it is
Loading
there.
the. Yeah, it
Okay,
is there. Yeah, it is there. You can search on
okay,
Google
okay,
and
okay, sure.
yeah. Just a moment. Let me just ping something. I'm not sure whether you have logged on from mobile, but let me just ping this to you. This is a YouTube video. You can have a quick look at this. It should work. But the only thing is, in higher versions, right? It is by default there. Now, because you have an older one, you will have to install it.
Yeah,
You have to download some exe file and do the installations there.
okay, sure, sure. I will do that. Okay.
Okay, Rohit. Then let's make a
Thanks, Pankaj.
close. If you have any questions, please do let me know. Yeah.
Okay,
Thank
okay,
you.
sure.
Thank you.
Thanks, Pankaj.